So I'm sorry about that. I'm not too sure what happened with my computer, but it decided to stop working. So we're going to have to do this in 2 parts, but we're halfway there. So this is a nice little chart that shows the different ABO genes that have been inherited, and it's based off of whether or not the secretor gene was also inherited. So the 4 listed up here also had secretor genes inherited along with them, whereas the bottom ones down here were non-secretors. So again, these secretor genes are inherited one from each parent. So the big S little e is from one parent, the big S little e is from the other parent. This right one here, we have the big S little e from one parent, and then the other parent must have been a non-secretor. But because we have at least one, it's codominant inheritance, so we're still going to have the secretor gene present. So because of that, these A, B, O, and AB genes that were also inherited are going to allow for our blood groups, our soluble antigens to be present in our secretions. So this is a substance chart, and so what this is showing is that if a person was an A blood type person and they did inherit the secretor gene, if we were to test any of their secretions, like their saliva or their tears, what we would find is that they'd have the A antigen as well as the H antigen, since H antigen again is the precursor to the A, in their substances. And then for the B, we'd have both B and a little bit of H. And then for an O, we know that O patients do not have the A antigen or the B antigen on their red cells, but they still do have H. It's just that the enzyme coding for the O gene isn't going to be able to add on any of the other immunodominant sugars. So we would still find H in the secretions, and then with AB, we would find all 3. Down here, because these are non-secretors, we would not find any antigens in their substances. This little arrow down here is trying to show you that although these 3 are secretors and we're able to identify their antigens in their substances, if for some reason one of these ABO genes were inherited along with the amorph of the H antigen, so if both parents passed along a little h to the offspring, regardless of whether or not they were a secretor, the fact that there's no H antigen, there's no possible way that the A antigen or B antigen could be added onto it. So we wouldn't find anything, even if they were a secretor, we would not find anything in their substances. And this is what I had talked about earlier, about how there's type 1 and type 2 precursors, and there are 2 potential precursors available. The type 1, again, is the beta 1-3 linkage of the terminal galactose to the second sugar, the N-acetylglucosamine. And then you could also have a beta 1-4 linkage, where the 1 carbon of the galactose adds to the 4 carbon of the N-acetylglucosamine. So ABH antigens are red cell antigens. They're derived from the type 2 chains, whereas ABH antigens in plasma and our secretions are actually developed from both types 1 and 2. So after fucose is added to the type 2 chain, the structure is actually termed a type 2H. And there's 4 different kinds of type 2H that have been identified. There are simple straight chain glycolipids, and then there's other branched chains. For the ABO subgroups, they're going to differ in the amount of antigen present on the red blood cell membrane. So we've already discussed the main ABO genes that can be inherited. Well, sometimes there are subgroups of those genes, and the main difference is just that less antigen is going to be displayed on the red cell, and that's what makes it a subgroup. Excuse me. And these subgroups are the result of a less effective enzyme. And they're not as efficient in converting the H antigen to A or B antigens. So because of this, there's going to be less A or B expression, and there's going to be more H antigen expression. And it is possible to have subgroups of both the A genotype as well as the B, and we're going to talk about both of them. So the 2 principal subgroups of A are A1 and A2, and the main difference is that these subgroups are going to possess, oh, I'm sorry, these subgroups are going to be more simplified and linear forms of the antigen as compared to the highly branched antigens of the original A blood group. So they are still going to react strongly with the anti-A commercially prepared reagent material that we're going to use. That's that blue reagent material that's supplied to us. However, if we were to use a specialized reagent antisera known as a lectin, and this lectin specifically is known as Dolichus biflorus because it is an anti-A1 antibody. And Dolichus biflorus is actually a plant that's able to produce this antibody that we want. So it's able to produce specifically anti-A1, not just anti-A. And we could use this specific lectin to test both A1 blood group people and A2 blood group people. And I'll show you in a second on a chart what the difference would look like. The important thing to know is that of the 100% of people who are going to react with the anti-A reagent and prove to be or possess the A antigen, whether they're a group A or they're a group AB, only 80% of them are actually A1, where 20% of them are A2. And about 1 to 8% of the A2 subgroup people are actually going to produce an antibody, and then about 22% to 35% of A2B individuals are actually going to produce an antibody. So that's the main difference. Why is the A2 phenotype important? The A2 and A2B individuals can produce this antibody like I was just talking about, and this antibody that is produced by these two subgroups, it can cause discrepancies in your reverse type because they might type like an A in the forward, but all of a sudden they have this anti-A1 reacting in addition to their anti-B. And it can also react with blood units that we're trying to cross-match for them, and so they would be incompatible as well. So what's the big difference between the two, between the A1 and the A2 antigen? The main thing is it's a quantitative difference. So there's more antigenetic sites available on A1 red cells as compared to A2. And the reason being is because the A2 gene, it doesn't convert the H antigen very well to A. So this results in fewer A2 antigen sites as compared to the many A1 antigen sites. And this is actually a beautiful chart that explains what I just said. So I'm going to have you look first over at the number of antigen sites per red blood cells. So as you can see, the A1 group versus the A2 group, the A1 group has the highly branched antigenetic sites, so they have a lot more antigen sites per red blood cell, as compared to the A2, which would only have about 250 times 10 to the third. It's more linear, and again, the H antigens on A2 blood groups are not going to be converted over as easily as the A1 is doing. So with that said, if we look at the anti-A antisera that is going to be used to test the patient's red blood cells, we can see that if we were to compare an A1 blood group red cell and an A2 blood group red cell, they're both still going to react with our commercially blue anti-A antisera, but the main difference is going to lie in that Dolichus biflorus lectin typing, which is the second second column right here. So this is actually the Dolichus anti-A1 lectin that they're using that was created from that plant. And when you test it with an A1, it's going to react because, again, this is an anti-A1 antibody. But if you test it with an A2 subgroup, it's not going to react because this A2 red cell has 0 A1 antigens. And then the other main difference is that if you were to use an anti-H lectin, which is another special reagent, it's also known as Ulex europaeus. If you want to know how to spell that, I did put the spellings of them down in the notes section of the PowerPoint. But essentially what you'll find is that an A1 blood type person is not going to react with the anti-H. And the reason being is because all of the H has converted over to the A1, Whereas A2 people, if you were to test with the anti-H, you would get reactivity because they A2 blood group people are not able to convert all of their H antigen over to A. And then, of course, with A group people, you would still see anti-B in their plasma or in their serum. But the main difference here is with the A2, as well as A2B people, they are able to develop an anti-A1 antibody. There are other A subgroups as well, although more infrequent. They have been described, and they involve a reduced expression of A antigens as well. The decreased number of A antigen sites per red cell can result in weak or absolute zero agglutination when tested with anti-A reagents. So this is genetic, and these are a list of some of the other A subgroups that are out there. There's A intermediate, A3, AX, AN, AN, AL, A Bantu. I have seen an A3 as well as a AN in my blood bank. And essentially, the way you pick it up is during the blood typing, because you would actually have a discrepancy in the forward and the reverse, and you'd have to determine whether, like, the reason behind it. And specifically with the subgroup A3, they actually cause mixed field agglutination when you're using polyclonal anti-A and anti-B. And this picture down here is a nice picture of the agglutination that you would see, as well as the free-floating cells or the unagglutinated red blood cells behind it. So this is mixed field. This is they definitely used a microscope to look at this. And then the other thing with the A3 is that they might possess an anti-A1 in their serum. But usually when we're dealing with these subgroups, what we wind up doing is what's called an adsorption and elution process, where we're actually able to take reagent antisera. We're able to take already manufactured anti-A and try and get it stuck onto the patient's red cells if there truly is an A antigen present. So I have done that process before. It's a little bit more specialized, but there are many ways to determine the subgroup that the person is. It just takes a little bit longer. So it's not as easy as a routine blood type. So that's the A subgroups. There are B subgroups, which occur a lot less frequently than your A subgroups, but they are possible. These B subgroups are differentiated by the type of reaction that they have with the anti-B reagent, the anti-A, B reagent, and the anti-H reagent. The criteria for the recognition and differentiation of these subgroups are similar to those of the A subgroups, but typically these subgroups demonstrate weak or no agglutination of red cells with anti-B reagents. So even though they're a B person, if we tested them with anti-B, they actually would show very, very weak or zero agglutination. So they might have a forward type that actually looks like an O person, and then their reverse type, they'd have an anti-A in their plasma, but then we'd be really confused and we need to figure out why that is. It might be because they're a B subgroup. Another ABO condition that is also possible is known as the Bombay phenotype. So we had discussed earlier the H antigen and the ability to inherit two recessive forms of that H, which would be the little h, little h. Well, when that happens, it's known as a Bombay phenotype, and it's designated O, little h. And it's this H, little h gene that is an amorph and results in little or no production of the L-fucosyl transferase enzyme that's needed to add that fucose onto that type 2 chain. So because of that, we don't have the H antigen. And originally this was found in Bombay, which is now known as Mumbai. It's very, very rare, but it is another possibility. Specifically, this Bombay phenotype, the little h will cause no H antigen to be produced. And then because there's no H antigen produced, it's not going to be able to produce A or B. So the patient is actually going to type in the forward type as an O. If we test the red cells with our anti-A, our anti-B, and our anti-H, it's going to be not reactive. However, what we will notice is that Bombay serum will have those antibodies in the plasma, because again, remember, they still follow the same Landsteiner rule. If the Bombay phenotype is not going to have those antigens, it's going to produce the antibody. So what we would find is that in the serum, it would agglutinate all ABO blood groups. It would even agglutinate donor blood that we would try to give them, because donor blood obviously would have the H antigen present, because 99.999% of the population inherits the H antigen. So what blood would we have to give a Bombay phenotype person if they needed blood? We'd have to give them another Bombay. Group O red blood cells cannot be given, again, because they still have the H antigen. And so you have to transfuse the patient with blood that contains no antigen. Now, this is very, very rare, and I do believe I read an article, I'm going to see if I can find it for you guys, of an Englishman who is the Bombay phenotype. And what he had to do was actually donate his own autologous blood and have it frozen at, I think, like -80 degrees, so that it's good for the next 10 to 20 years in case he were to ever need blood, because it's so, so rare. So now we're going to move on and discuss each of the ABO antibodies and look at its importance. As we know, we understand Landsteiner's rule that healthy individuals will possess the ABO antibodies to the ABO antigen that is absent from the red blood cell. And this was the first to be identified because it's actually the most significant for transfusion practice. It's the only system where the reciprocal antibodies are consistently and predictably present in the sera of people who have never had exposure to human red cells, because the rest of the other antibodies that we will be discussing have been produced because of some exposure to a foreign antigen. They've had an immune response to them, but this is the only blood group system where they don't need to have an immune response, they just have them. So most blood group systems are made up of an antigen on a red cell, and in the absence of its corresponding antibody in the serum, if you do not have a particular antigen on your red cell, then it is possible to elicit an immune response that results in the production of the antibody specific for the missing antigen. So remember that the ABO blood group system does not require the presence of a foreign red blood cell for its production of ABO antibodies. The ABO antibodies are non-red blood cell stimulated, and they're a result of probably environmental exposure, and so they're often referred to as expected antibodies or naturally occurring antibodies. If we were to do a titer of the ABO antibodies found in our plasma and serum, it would be very, very high right now, but as we start to get older, we'd see a decline in that titer result, and we'd also see a decline in the number of ABO antibodies in patients who have immunoglobulin deficiencies, such as hypogammaglobulinemia. Also, these ABO antibodies are not produced until you're about 3 to 6 months of age, so infants would not be producers of antibodies. And when we start to test cord blood specimens, you'll see that we don't even do a reverse type on babies. We only do a forward type. So here's the chart in case you were wondering, well, what are the blood type frequencies in the population? Well, here you go. O is the most common blood type at 44%, followed by A, which is about 43%, then B, and then AB. And there's the respective antibodies that you would find in the serum. So now we're going to take a look at each of the different antibodies. So this first one that we're talking about is the anti-A1 antibody that you would find in a person who was a subgroup of A. So group O and group B individuals contain anti-A in their serum. However, the anti-A can be separated into two different components, anti-A and then the anti-A1. The anti-A1 would only agglutinate the A1 antigen, not the A2 antigen. So this is our Dolichus biflorus lectin type. It would only react with the A1 antigen and not the A2. So please start to associate the anti-A1 lectin or the Dolichus biflorus as definitely being something different than the blue anti-A reagent that we're going to have in our racks. Another thing to note is just that there is no such thing as an anti-A2. So there's only anti-A and anti-A1. This anti-A1 is an IgM class that can only be clinically significant sometimes, so it can cause intravascular transfusion reaction, but not often. The thermal range for this antibody is about 4 to 22 degrees Celsius, and this equates out to be room temperature. And then it does not have an effect with hemolytic disease of the newborn, so it will not cross the placenta, and you should know that because it's an IgM pentamer, so it's too large. Next antibody we're going to talk about is anti-A, B, and so this antibody is found in the serum of group O individuals. It reacts with A, B, and AB cells. It's predominantly IgG, and it has small portions of being IgM. And what you need to remember is that this anti-A, B is actually one antibody. It is not a mixture of anti-A and anti-B. It's actually a cross-reactive antibody that's capable of recognizing a particular antigenetic determinant common to several molecules. So this distinguishing characteristic enables the antibody to agglutinate with A, B, and AB phenotype. For the ABO antibodies in general, the IgM ones are predominantly going to be found in group A and group B individuals. So your anti-A that you will find in your reverse as well as your anti-B are IgM. And then your IgG with some IgM is going to be found in the group O individuals. So us group O individuals, we actually have 3 different types of antibodies in our plasma. We have anti-A, B, and we have some anti-A and some anti-B. Now, this anti-A, anti-B, and anti-A, B are able to bind complement. The main difference is that, of course, the IgM antibodies are the pentamers, so you only need one molecule to activate the complement cascade, whereas the IgG anti-A, B, you would actually need a couple of them. They are, again, in high titer, so they react very, very strongly. You should be getting like 4 pluses and 3 pluses in a person's reverse type. If not, then they must have some other type of clinical condition or they're very old. The clinical significance of these ABO antibodies is very, very high, and as you can see why, it can cause an acute hemolytic transfusion reaction. It can occur both extravascularly as well as intravascularly. An acute hemolytic transfusion reaction is hemolysis, and it's characterized by a rapid onset of fever, chills, hemoglobinemia, and hypotension, and it can develop into major complications such as shock, renal failure, and disseminated intravascular coagulation. What makes these capable is that they are able to react at body temperature, which is 37 degrees. So they react at room temperature, and they can also react at 37 degrees. And they're also, well, specifically the anti-A, B is able to cross the placenta and cause hemolytic disease in the newborn. So the ABO antibodies, as I said, are expected, but they're usually present only within the first 3 to 6 months of life. So that's when they first start to develop. You wouldn't see them prior to that, which is why we don't test cord blood for reverse typing. They're stable by ages 5 to 6 years of age, and then they decline as we get older, and their levels start to decrease also in hypogammaglobulinemia. Newborns may passively acquire maternal antibodies, So we will do sometimes type in screens on baby blood, and if the screen were to come up, it's actually not the baby's antibodies that we're finding, it's the mom's IgG antibodies that we're able to cross the placenta. And so just remember that there are two different types of antibodies. There's non-red blood cell stimulated antibodies, such as these ABO antibodies, which are expected, and then there's red blood cell stimulated antibodies, which are going to be the majority of the other antibodies we discuss, because they are results of being exposed to foreign antigens through transfusion or pregnancy, and they're usually IgG, and they usually can be very active at our body temperature of 37 degrees. They can occur in group O patients, and then they may occur in group A or B patients as well. And these antibodies occur in other blood group systems. And then this last slide that I want to show you is the difference between an autoantibody and an alloantibody. So an autoantibody is different because it's actually directed at the patient's own self-antigens, whereas the alloantibody is directed against foreign antigens. So what you'll notice is that in this case for anti-H, the auto one is not very clinically significant. It has a low thermal range of only room temperature. It will not cause hemolytic disease of the newborn, and it will not cause hemolytic transfusion reactions because it's an IgM molecule. And then the allo anti-H, which is created in the Bombay phenotype, is very clinically significant. As you can see, it can cause hemolytic transfusion reactions, and it is capable of crossing the placenta because there is an IgG component to it, and it's able to react at body temperature of about 37 degrees. So this wraps it up. I'm sorry that there's two different slides, PowerPoints for this. It just it shut off in the middle of it. So here's your ABO, H, and secretor genes. The next one we're going to talk about is RH.